You see the term high energy? In addition to thinking of me, think of unstable, reactive, things like the bonds in ATP.
Energy is the ability to do work. Everything from propel a ball down a hill to get a reaction to happen when you break a molecule of ATP, as we'll talk about. Bottom line, when things have energy, they can do things. Everything from exciting things like reacting and breaking bonds to more boring things like just relaxing. You can think of high energy molecules as being kind of uncomfy. Just like when you're uncomfy, you might be wiggling around and trying to get comfy. When molecules are uncomfy, they're going to be moving around, they're going to react, they're going to do whatever they can do in order to get comfy. So molecules of high energy tend to do things that are going to then release that energy. And once they've released that energy, they've used their energy to do stuff, they don't have energy to do more stuff. And therefore, things tend to be in a low energy state. You're more likely to see a ball at the bottom of the hill than to see a ball at the top of the hill, assuming that there's something that's going to tip the ball over the edge of the hill, as we'll talk about. When we're talking about G, when we're talking about energy, we're typically talking about the Gibbs free energy, or G. More specifically, if we want to figure out whether a reaction will be what we call spontaneous, whether it's a favorable reaction energetically, we want to look at the delta G. What delta stands for change in. So this delta sign is like triangle. A reaction with a negative delta G means that the reaction is what we call spontaneous. That doesn't mean likely, it just means that it's energetically favorable. It means that the products are going to be at a lower energy state than the reactants. So it's say if we had a reaction with the ball at the top of the hill, this would be we would have a G here, and we would have a G here, and the delta G would be the difference in the G. So we'd have the energy of the products minus the energy of the reactants. And because the products are going to be at a lower energy state, we're going to have a negative delta G, and this is going to be favorable. If we were to look at it in the opposite direction, if we were to subtract the energy of down here from the energy of up here, we would have a positive delta G, and that would be unfavorable. So it's unfavorable for the ball to fall up the hill, but it's favorable for the ball to fall down the hill. I talk much more about this in my thermodynamics posts, but whether or not a reaction is spontaneous depends on the contributions of entropy and enthalpy and temperature. Enthalpy is whether the reaction will give off heat. It's kind of a measure of the bond energies. And then entropy is a measure of freedom or disorder. So much more on this in other posts. But when we say a reaction gives off energy, we say it's exergonic. When we talk about energy in biochemistry, one of the molecules that we talk most about is ATP. Now, ATP stands for adenosine triphosphate. So you have this like RNA letter where it has these 3 phosphate groups. And for now, just know that these phosphate groups are negatively charged. Like charges repel one another. And so having these negatively charged molecules this close together is really unfavorable. It's going to be hard to hold them together, kind of like it clamps spring. Just like it takes energy to kind of keep that spring clamp together, it takes energy to hold those phosphate groups together. And the energy is held in these bonds. And so we call these bonds high energy, or because they have this high chemical potential energy. Now, if you were to break one of those bonds, you're going to release some of that energy because you can't lose energy. You can just kind of use energy. And so you can use that energy in order to do things. This can be boring things like just kind of move that phosphate group off, or it can be more exciting things. Like say if you had a ping pong ball at the bottom of the spring and you were to release this spring, the ping pong ball might fly across the room. Similarly, we can couple the breaking of ATP to other reactions in order to get reactions to happen. And we'll talk much more about this in a minute. When we break ATP, not only do we get the benefit of kind of releasing the negative charge repulsion, But you get greater what we call resonance stabilization. Basically, the electrons are happier in this state because they can be shared more evenly. It's outside the scope of this post. And this also has better hydration than ATP, so it can be surrounded by more water molecules, which again is going to give you some benefits. And so much more on this in my post at ATP. I just wanted to give you an example of where energy comes into play and where you might see this term high energy bonds. In a little more detail, it can get kind of confusing because every time we talk about breaking a bond, we're going to have to put in a little energy. That is, the breaking itself is going to be endergonic. It's going to require energy, but this is just for the breaking point. And if the bond is weak or unstable, the required energy is going to be small. So when we talk about the initial breaking of that ATP, when we talk about breaking off that phosphate group, that's going to require a little bit of energy. It's going to be endergonic, but because that bond is fairly unstable, it's not going to take that much energy to do so. And overall, the reaction is going to be highly exergonic, energy releasing, because the bonds and interactions in the molecules that form are lower energy. And when we're talking about whether the reaction will be exergonic, we have to compare the starting energy to the finishing energy. So we need to look at the delta G. And if the end products are much more stable, the energy that's going to be released is going to be large. And this is true in the case of ATP. The products are going to be at a much lower free energy than the reactants. And therefore, the bond is going to, we say this bond is high energy. And when you break that bond, you get that energy, you get that release of energy. The reaction is going to be exergonic. So if the bonds and the interactions and the molecules that form that are in your products are more stable than those in your reactants, you're going to end up with the reaction being exergonic or energy releasing overall. Now, when we talk about these interactions, they can also include things that are less obvious, things like solvation, so intermolecular interactions with water. And therefore, even if you don't see new bonds in the equation, there are hidden reactions going on that you need to take into account. And this is going to influence that delta H in our free energy equation. Something else is also going to come into account that's going to affect our delta S. And delta S is entropy, randomness, or disorder. So you get entropic benefit from increasing the randomness or disorder. And what can happen is that when you have a molecule like ATP break, you're generating more molecules. And when you generate more molecules, you're introducing entropy. And so you're getting better hydration, which is going to influence that enthalpy. And you're going to get more molecules, which is going to influence your entropy. And thus, overall, this reaction is going to be highly exergonic. It's going to be energetically favorable. Delta G can be kind of deceiving. It talks about whether a reaction is spontaneous, whether it's thermodynamically favorable, but it doesn't tell us whether a reaction is actually going to happen. Whether a reaction is actually going to happen is going to depend on things, including how much of an activation barrier is required. Delta G is what we call a state function. It only depends on the energy of the reactants and the products, the energy of the initial states and the final states, and it doesn't take into account anything that happens in between. And typically something has to happen in between. You have to put in some energy to get over an activation barrier. So you don't see it, but instead of the ball just being at the top of the hill, the ball is kind of more like on one side of a rainbow and it has to go up before it can get to the pot of the gold on the other side. Similarly, you need to provide energy in order to get a reaction to happen. You can think of it in terms of kind of if you go couch shopping and you might be on an uncomfy couch and there might be a comfy couch across the room. And you might be happier in that comfy couch. You'll have a lower free energy there. You'll be less squirmy, more comfortable. But in order to actually get to that more comfy couch, you have to get up off your bottom and move across the room. You have to put in that activation energy And therefore there's this barrier for you getting to the other side, but you're still going to be just as happy on that other side as if you were to be like teleported over there. And so the reaction would still be what we call spontaneous as long as the delta G is negative. But there could be unforeseen barriers in between getting there actually. Now, in order to get there more easily, we would like to teleport across the room. And well, we can't get molecules to teleport, but we can make it easier for them to react. And this is going to be the case with what we call enzymes. Enzymes are going to lower the barrier that's needed in order to get past that activation hump. So they lower the energy of activation. And this can be important because it can allow molecules to reach that lower energy state. It can allow them to reach that place where they're more happy, they're more comfy. They just didn't have before the energy in order to get over that activation barrier. So we see enzymes a lot in biochemistry. Enzymes are what we call catalysts. That means that they speed up reactions without being used up in the process. So they can be used over and over and over again. And what they're doing is they're just lowering the activation barrier. You can think of it kind of like if you were to try to break a stick, the enzyme could kind of hold it in that awkward state where it's about to break. It can help stabilize awkward intermediates, hold molecules in place, all this cool stuff in order to help reactions happen. Now, sometimes enzymes get a little extra help using breaking of ATP or another high energy bond in order to couple the energy release from that reaction with another reaction, such as polymerization of nucleotides, so kind of linking together DNA letters. As we talked about, when you have those phosphate groups break apart, you're going to be releasing energy, and this energy that's released can be used to drive unfavorable processes, like the linking together of DNA bases, which is limiting the freedom of those bases to move around, and therefore is going to require a little energy in order to get this reaction to happen. Now, this brings us to another important point, is that molecules, when they have energy, they move around, and everything wants to move as much as possible. However, it takes energy to move. When we talk about heat, this is kind of like kinetic energy and the energy of movement. At a higher temperature, molecules have more heat. They can move around more. How much they can move around is going to depend on things like how stuck they are to other molecules. So electrostatics, basically the idea that opposite charges are attracting, can make it harder for molecules to break free from one another. Additionally, you have things like steric hindrance, where things can't occupy the same place at the same time. So there's going to be barriers to movement, but when molecules have energy, they can move around. And so sometimes they might use their energy to do more boring stuff, like kind of just wiggle around, instead of doing more exciting things like reacting. But the more energy it takes for these molecules to do things, everything from move around to react, the less likely it is to happen and the more stable it is currently. As a result, molecules can kind of get stuck in what we call low energy states. And sometimes this is good and sometimes it can be not so good. This comes into play with protein folding. When a protein folds up, it does so in a way that's going to be most energetically favorable, at least as far as the molecule can see. What can happen is that the molecule is going to fold up in order to kind of like minimize its free energy. And when you see computer functions like try to optimize a reaction, they'll try to optimize to have the lowest free energy to get the molecules in kind of their happiest state. But what can happen is that when these molecules fold up, there can actually be multiple low energy states. So multiple states in which this molecule is really comfy, but then there can be barriers to getting between those different states. And so you see this sometimes when we're talking about protein purification. This was an example I took from my post on when proteins crash out during purification, or basically they fail to bind properly, or they unbind and then they kind of clump up. Now, that clumped up or aggregated form, this is a low energy state. So the molecules are kind of happy that way, but you're not very happy that way. But there's another happy state, the one state that you're more happy with, and this is when the protein is properly folded. But in between, there's going to be a high energy state where the molecule is unfolded. In order to get from that aggregated low energy state to the folded low energy state, you have to go through that high energy unfolded state. And this is going to make it harder to get from one state to another. And this is why you typically would have to put in some sort of energy, maybe heat the molecules up, or you'd have to add some sort of chemical to lower the unfolded energy, add denaturants like urea or detergent in order to lower the cost of unfolding in order to get the protein to be able to see the folded state. Similarly, in software programs, they might do things like simulated annealing, where basically they add virtual energy in order to try to get molecules out of these kind of these free energy minima, where they're kind of trapped at a low energy state without realizing that there's something better over the hill. Another time we see energy come into play is when it comes to nucleic acid binding and things like the temperature of melting or the TM of primers. In PCR, what we're doing is we're using small pieces of DNA to target regions of DNA to be a template DNA in order to be copied, and much more on this in my post on PCR. But when you design those short pieces of DNA, specifying where you want to copy these pieces of DNA, we call primers. Those primers are going to bind specifically to regions of DNA. And the stronger they bind, the harder it's going to be for them to unbind. And when we talk about unbinding, we're going to be requiring energy. And we're going to need the more tightly they're bound, the more energy it's going to take to get them to unbind. Because remember, it's going to take energy for them to move, and we have electrostatics and things like this, where we have partial charge attractions through hydrogen bonding, holding those primers in place. And so the more tightly they're held, the more energy we're going to need in order to break them free, and thus the higher the temperature. The higher the temperature we're going to need in order to get them to come apart. So when we design these primers and we set up our PCR reaction, we have to take into account how strongly these primers bind when we're determining what temperature to use for our annealing temperature. When we're talking about annealing, this is where we're actually getting the primers to bind to the DNA. And we want to use a temperature that's going to be high enough that we're not going to just get non-specific binding. So we're not going to get these primers binding just anywhere. We want them to only be able to bind if they're strong, the interactions are strong enough to withstand the temperature. But we don't want the temperature to be so high that the primers can't stay stuck to the sequences we want them to stick to. So here comes into play that temperature of melting, the TM, the temperature at which half of the primers will be bound at the correct site. And we can take this into account when designing our PCR reaction. So again, we're seeing this idea of energy come into play. And the thing to keep in mind is that the more energy molecules have, the more they are able to do things, everything from move to fall off the, say, to fall off your DNA, to get reactions to happen. Remember, when you see high energy, think of uncomfy molecules, molecules that are wanting to react. They're wanting to do things in order to give off that energy, in order to get more happy. Just like you might be more happy in one of those memory foam couches, but you might also be less likely to get up and go move. It might be kind of harder to move because you're all kind of sunk in on that memory foam. When molecules are in a lower energy state, they're more comfy and it's harder for them to do things. They don't have the energy to do any more things. They've kind of spent their energy cache. And when we talk about energy cache in biochemistry, we're often talking about ATP, which is the classic example of a high energy bond. These bonds are what we call high energy. They have high chemical potential energy, meaning that if you were to break one of these bonds, you're going to get some of that energy back, and you can use that energy to drive reactions that aren't very energetically favorable. So when we talk about energetically favorable, we're talking about a negative delta G, but just because something has a positive delta G doesn't mean that it can't happen. And so just like the ball isn't going to spontaneously fall from the bottom to the top of the hill. We can push it up the hill, and we can use the energy from reactions from the breaking of ATP, say we can couple this to unfavorable reactions in order to get those reactions to happen. Another important point is that just because a reaction is favorable energetically, that's only taking into account the reactants and the products and not any sort of in between. So we need to think about the whole rainbow rather than just the pot of gold on the other side. And to lower the energy required in order to get to that pot of the gold, in order to get to the products, you have to go over an activation barrier, and this barrier can be lowered by molecules called enzymes. And so we see a lot of reactions being catalyzed or sped up by enzymes in biochemistry. And beware of local minima, where basically reactions can get kind of fooled into thinking that there isn't anything better out there because they can't see it due to a higher energy state. Hope that helps you understand how energy comes into play in biochemistry.